Well, good morning and welcome back. Hope you had a good orientation on the Discord software as part of the webinar. It's been, we're going to capture all of this discussion. It's just been an amazing discussion. I always say a lot of times the extra speaker is the audience with their insight and experience and not just the speakers. But so welcome back. And the second session, we're going to start going into, we had a great first session discussion on data as a foundational layer. Now we're going to have some real applications of data and using machine and deep learning. So two of the best people in this area we're lucky to have on this panel. We'll start with Dr. David Albert, who is the founder of AliveCor and have had personal great experience with AliveCor. And he's going to tell us about AliveCor and picking up signals from the noise of data. David?
Thank you, Anthony, and it's a pleasure for me to be on this webinar. Just for all of those, I have disclosures, and while I still keep a hand in academic medicine, you can discount anything I say, but this will not be an ad, I promise. The chairman of my board and a very famous venture capitalist, Vinod Khosla, has, several years ago said that 80% of what doctors do will be done by AI in the future. Now, as he would say, he's not very good on dates, but he's very good on direction. So it may not be 2025, but sometime in the future. I like to call it not artificial intelligence, augmented intelligence. And that we will be the beneficiaries, we being physicians, nurses, other caregivers, be the beneficiaries of machine intelligence helping us to better and more efficiently care for patients. And so everybody's seen the Gartner hype cycle. And where in that Gartner hype cycle, excuse me, AI in healthcare, we're you're right at the top, and you hear, cloud-based, deep learning, machine learning, all of these things are hot topics. And as we've been in a pandemic and a lockdown, remote medicine, telecare have become much more important. So this seminar is a reflection of the rest of healthcare. Both my oldest son, who runs the COVID service, he's co-lead of the COVID service at Cedars-Sinai, and my wife is a rheumatologist faculty member at USC. So we're, as we say in America, lousy in doctors in our family. They would tell you that telecare has been important in delivering care. And I think it's not going to go back the way it was in January. So what we'll see is you've got cardiology needing more AI. AI in 2020 means deep neural networks, better known as deep learning. Deep learning requires a large quantity of accurately labeled data for what we call supervised learning. Yes, Jan LeCun says the future will be unsupervised, but today, supervised learning, whether it's X-rays, MRs, CTs, EKGs, need to be labeled so that we can train the machine, or it can train itself. In cardiology, we have many imaging modalities, from CT, MR, echo, PET, nuclear, you name it. And we also have this, the EMR data, unstructured data, lab values, all kinds of things. But my area that I focused on is the electrocardiogram, and with my partners, and I've been fortunate enough to partner with the Mayo Clinic and Dr. Paul Friedman, Dr. Mike Ackerman, Dr. Peter Noseworthy, and their team there in sharing data and sharing techniques and teaching each other. The ECG is 100 years old, over 100 years old, 120 years old. And Wilhelm Einthoven first developed it and showed us how to measure the limb leads. And here in 2020, this technology that's over 100 years old is just as relevant, if not more relevant than it's ever been. And so, as I said, deep learning requires massive data sets. And my friend Eric Topol in his book, Deep Medicine, talked about my company AliveCor and many other examples of how this deep learning and basically multi-layer neural networks are going to help us, because they've already shown their value, improve the delivery of care. And so I'm going to talk about it. Well, I said you need a lot of data. In our cloud at AliveCor, we have over 70 million rhythm strips going back 10 years to when I started the company in 2010. And a lot of that data is longitudinal. So you have people who've been recording their ECGs literally for years. And that kind of data is the kind of data you need to do deep learning. And so, just last month, we had 2.2 million ECGs recorded into our cloud, and they were recorded from lots of different people. So 2.2 million coming from over 200,000 different people. So as you can see, the average user, 10 to 20 ECGs, it is a big database, and we have about 1 million unique users have recorded those 70 million ECGs. So this begins to be big data. And so what we know is you've got to have lots of data so that you can generalize solutions, so that they can converge. The deep neural network can converge on a solution, on a unique solution, without overtraining, which unfortunately can still happen. These are not magic. And so the laws of analysis still are important. And so if you don't have enough data to generalize, to represent what I call the RW, the real world, you still have the potential to overtrain your data, overtrain your models. And so, we're going to talk about a number of different methodologies. We use both convolutional neural networks and other techniques, support vector machines, all kinds of things. And I'm going to go into each one of those when it comes to the specific applications. And to be honest with you, this is not going to be a technical talk about that, because your eyes will glaze over and they'll roll back in your head and we'll all go to sleep. So I'm going to talk about the applications. Now, a lot of people out there were thinking, well, we've had computerized ECG interpretation for 40 years, more. That's correct. And those have been traditional time domain signal processing methods where we detect features, P waves, QRSs, T waves. We check beat morphology, left, right bundle, PVCs, PACs, normal sinus beats. And we have libraries that say, well, if it's an NV, normal ventricular, it's ventricular by Gemini. So that technology's been around, and anyone who overreads public ECGs knows that it is far from perfect. But it told us what we as experts could see with our eyes. That's by Gemini. That's a run of VTAC. That's first degree AV block. That's Wanky block. It did not tell us things that we couldn't see or measure. So in this presentation, I'm going to talk about how deep learning can enable us to detect the invisible. And so some of these things have not been cleared because the FDA is still, learning how to deal with deep learning and AI. So here's an acute MI. You can see an anterior MI. You get tombstones in V2 through V4. And this is a STEMI, call code STEMI. It's time to get this guy to the cath lab and open up that artery, probably LAD. Here's a run of VTAC. VTAC, the patient monitor goes off, charge the defibrillator. Time to call a code on this person. These are things that we've traditionally done. Now, what I'm going to talk about is things that we don't do today. And why? Well, there are not enough cardiologists. And if you think it's a problem in the United States where we have 30,000 odd cardiologists and electrophysiologists, imagine what's like in India with 1.3 billion people, or China. That's a problem. And therefore, I'm back at my AI being augmented intelligence. We need help. And we need to just take data and distill it into actionable information. So my partner's Dr. Paul Friedman, who is the chair of cardiovascular medicine at Mayo Clinic. These slides were provided by him, and we've had a multi-year collaboration with Mayo on deep learning and AI as applied to electrocardiograms. And by the way, full disclosure, the Mayo Clinic is an investor in my company. Just want you to know. ECGs, painless, inexpensive ways. But can you look at that ECG and say, is the ejection fraction under 35%? Does this patient need an echo? Well, I can't. But a deep neural network can, with really amazing accuracy. And the Mayo Clinic has published data. And so they're showing their 12-lead ECG data combined with their echo data. So here's where you take two large data sets and you use deep learning to merge the information. So the input is 12-lead ECGs and the output is echo-based ejection fractions. And you let the deep neural network find the correlation, because that's what they do. They are pattern recognizers, deep neural networks, and they find correlations. So again, this is the type of tech that I'm not going to go into, and I'm sure other speakers will, but what you'll see is this notion of how do you take a convolutional neural network, which can, has done amazing things on both speech recognition and image recognition, whether it's Google Photos or Alexa, this has shown us the power of these deep neural networks. And now we're beginning to apply them, whether it's to dermatology or radiology or cardiology. Apply this power to augment us. And as somebody said, deep learning is not going to replace radiologists. Radiologists who use deep learning will replace those who do not. And so the Mayo Clinic turned this big data warehouse into a machine, literally, that can generate new insights. And they used a convolutional neural network, and they tied ECGs to ejection fraction. And how was it? Well, pretty dang good. Area under the curve, the AUC for predicting low ejection fraction, less than 35%, has an AUC of 0.93. And that is outstanding. So you can take a 12-lead ECG, and they've even applied it to single-lead ECGs, just slightly less accurate, I think AUC of 0.9, and said, we can screen people with this very inexpensive tool and figure out the people who need to go get an echo, need to go get an MRI. And that's exciting. And everybody knows point-of-care ultrasound is here today. And so you can really improve efficiency when it comes to detecting these people. So what happens if it says you have a low ejection fraction, but the echo says your EF's 50? Well, guess what? It looks to the future. You have 5 times the probability of developing a low ejection fraction in the next 6 years, and 6 or 7 times over 12 years. So it's actually seeing something that says you're going to have a problem. And in medicine, prediction is equivalent to prevention. So we can put these people, we can up our vigilance on them, we can change their lifestyle. We may be able to prevent the inevitable problem they have with their left ventricular function. So does it help if we add age and gender to this? And the answer was no, it does not. And as a matter of fact, they were able to show that with like 98% accuracy, they get a 12-lead ECG and at Mayo Clinic decide if you're a man or a woman. Now, I'm not going to get into gender. That's a complex subject today. But they've also applied it with us on some other features. So not just low ejection fraction, but hyperkalemia. And we've had an ongoing project, published a paper in JAMA Cardiology, presented at American College of Cardiology, the ability to detect hyperkalemia. So whether you're a patient getting a RAS drug for heart failure, whether you're a patient with CKD stage 3 to 5, or whether you're a dialysis patient, hyperkalemia is a very big problem, and today we have some medications that are far more effective and less troublesome to lower serum potassium. And so this becomes urgent. And if a patient at home, if everybody out there who knows how dialysis works, it's 3 times a week, Monday, Wednesday, Friday, and then you have a 2-day hiatus, or it's Tuesday, Thursday, Saturday, and a 2-day hiatus. And as we know, almost 25% of dialysis patients die every year. So, and they have a huge burden of arrhythmias. And when does it mostly happen? That second interdialysis day. And so if we could detect the potential hyperkalemia and the arrhythmias it causes, that would be very useful, because potentially we could get them either medication or even additional dialysis. So that is a project we've been doing, and again, seeing something that you cannot see. Okay, this was the age and sex, a little out of order, I'm sorry. But as you can see, an incredible AUC of 0.97 to determine, he said sex, I'll call that gender. This is a really interesting patient. What you had here was a patient who was in their late 30s, whose ECG age was 50, and it kept going up almost to 70, and then it had a dramatic drop. And then it even dropped further. And can anybody imagine what happened here? Well, what happened is the patient had a heart transplant. They had a cardiomyopathy, and the ECG picked that up. And then when they had a heart transplant from someone who their heart age dropped dramatically, and then they got religion and they changed their lifestyle, and it dropped even further. And so this is a great example how the ECG didn't just detect poor pump function, but was able to track it over time. So really an exciting application of our old technology. Okay, look at this. 72-year-old man presents with embolic stroke, a cryptogenic stroke. Okay, I'm going to put an ILR in them. What are we going to do? Do we give them aspirin because, you know, we think it comes from the neck, or are we going to give them an anticoagulant because it comes from the left atrial appendage? It's a classic problem. Neurologists involved as well as cardiologists. And today, you know, Crystal Leia told us put a loop recorder in, put a link in. But what if you could tell that that patient had AF without having to put in a very expensive monitor? And so the Mayo Clinic looked at sinus rhythm ECGs to try to predict that somebody had previously AF. And obviously that would be very useful if the sinus rhythm ECG gave you insight. And it did. So you had almost 90% AUC, 0.9 AUC of predicting AF in a patient from a sinus rhythm ECG. Again, we know things, PACs, P wave duration. We know that there are features that have been associated with AF, that have been associated with an enlarged atrial, P waves in V1. But this actually quantifies that using deep neural networks. So another very exciting application. So this patient had AF, goes on, Xarelto, Eliquis, whatever. Now these next slides were provided by Philips, by the head of their advanced algorithm research, and I talk about the work they're doing, because every medical device company has efforts at deep learning. And so, what they've done is they've also looked at AF using deep learning, and again, recurrent as well as convolutional neural networks. And I won't go into this, but these are all published studies, and had very good F1 score, which is a combination score of 0.82, which is an outstanding F1 score in terms of sensitivity, specificity, positive predictive value, and negative predictive value. So they also did a review of all the research that's being done, all the papers that are being done on deep learning. And this has been published in the Journal of Electrocardiology, and they found 52 papers. But this is what's really important is look at the graph on the left. The number of papers is going up exponentially. We're right up there at the peak of the Gartner hype cycle, and the interest in the power of this versus conventional signal processing is outstanding. Now, these next slides are from my company. As I said, the things I've talked about previously were other people, and I didn't want this to be an ad. This is education. And so these are about things we're doing. We published a paper with Dr. Rod Patzman, the head of AFib research at Northwestern, in Circulation Electrophysiology this past year, June of 2019, on continuous AFib monitoring using a wrist-based device, and the ability with a wrist-based device to quantify AF burden, which is very important if you're deciding, 30 seconds of AFib in a person with a CHA2DS2-VASc of 1 is probably not a good anticoagulation subject, but 5 days of AFib, even in a CHA2DS2-VASc 1, starts to move you to anticoagulation. And so we were able to show in that paper and in that study, here's a perfect example, that the blue line is the heart rate from the optical, the PPG heart rate from the wearable. And the red dots are ECG rhythm strips, 30-second rhythm strips collected by the Cardio device that are recorded that are AFib. And a green dot represents sinus rhythm. So that's automatically defined by our device. And you can see that in the middle of the night, somewhere a little past 3 in the morning, this patient went into atrial fibrillation and sustained. So you see not only did their heart rate go up, but the heart rate variability, irregular pulse increased. And then sometime in the morning, right around 9, they went back into sinus rhythm. And so this was all tracked using a device, and you can tell exactly what the AFib burden was. It was 5 hours and 45 minutes. So this is exciting. Why? Because potentially we can expand long-term monitoring beyond 10 days, 30 days. And today, the only kind of continuous long-term monitoring you have is an implantable loop recorder, not a non-invasive, not inexpensive. So this would really help expand our long-term monitoring and enable, here's another example from our paper in Circulation EP, showing the duration of AFib, showing where a patient went into AFib, documenting not only the sinus rhythm ECGs, but the AFib ECGs. And so really a potential interesting thing. I talked about this earlier, 2.8 million ECGs with 4.3 million serum potassium values, developing a deep neural network that correlates the two. And that is exciting and ongoing work, not FDA cleared yet. But again, we use a deep neural network to associate the serum potassium value and the ECG. Very exciting. Now, this is something that's actually going right now. So we've been working with Dr. Mike Ackerman in the Congenital Arrhythmia Clinic at Mayo Clinic, and we used millions of ECGs that have QT measurements to take our Cardiac-6L, our 6-lead ECG, and have it detect QTC. And today, we've received an emergency use authorization, and our Cardiac-6L, in combination with Mayo Clinic, is being used to detect prolonged QT in patients taking hydroxychloroquine and azithromycin. And as we saw in papers from JAMA and Heart Rhythm a week ago, Leo Jankelson's group at NYU Langone published in Heart Rhythm, and another group published in JAMA showing significant QT prolongation in patients taking that combination of 2 drugs known to prolong QT. And obviously, there's studies ongoing trying to evaluate the efficacy of that therapy. The last thing you want to do is hurt somebody with Torsade, which they documented. Jankelson's group showed a great example of on the ward at NYU of Torsade caused by QT prolongation of those 2 medicines. And so they're using, a number of centers all over the world, quite frankly, are using our 6L right now to monitor QT acutely. And we received an emergency use authorization. And that was because we've got papers published, we've got more in the works. And we hope to have a tool that a patient at home or a pharmacist or a psychiatrist or an oncologist could use, not FDA cleared for general use yet, but could use to monitor QT, because there are a lot of very effective medications that happen to be a hERG blocker and be a QT prolonger. And so that's another application of deep neural networks, taking what's been traditionally a 12-lead ECG measurement and using half the 12 lead ECG, the 6 limb leads, to give you the same thing. And I can tell you, we presented this last year at Heart Rhythm. It's an exciting application. Now, another thing we do is we identify you. When you use our device, the first 30 times you record, it'll say, was this you, David? Was this you, Anthony? And what it's doing is building its own convolutional neural network of what your ECG looks like. And that includes your rhythm, your morphology, all the features. And if you have bouts of AFib during that time, it says AFib, sinus rhythm, both are normal for you. So it develops a full network. And here's a patient that stays in the same morphology. And by the way, Anthony, I'm going to show you a great example. Here's another patient. What happened? This patient developed an incomplete right bundle branch block. So, you know, and their ID went down, and it said something changed. So this has the ability to pick up. Now today we don't use it clinically. We do use it so that when we send data to your doctor, we don't send your grandfather's data. We don't send your child's data that you may have lent your device to. We want to make sure they only see your data. And so this has been very useful. Here you see a patient that goes in and out of AFib. And what happened at the time? They bounced around, but then somewhere in you know, early 2016, they became predominantly very low correlation. Well, what happened is they developed an ST abnormality. And I don't know who these people are. I only have anonymous access, and I hope they seek help. But the point is, potentially, this could be used clinically. And so this just shows you we do what's called dimension reduction. So each one of these clusters you see, this is a three-dimensional space. Each one of these clusters represents, in different colors, represents a different person. And you can see some are more diverse and more expanded. This one on the left that's yellow is there. So with that, I will say thank you and turn it back to you, Anthony.
Thank you, David, for not just a great talk in terms of talking about application, but also just introducing some very key concepts and we can all learn from. So thank you very much, David. We're going to ask you to mute yourself and get yourself off camera, and then we'll bring on Rob Brisk, who is an amazing young cardiologist that I had the fortune of meeting in London. He's a adult cardiologist, but also a machine and deep learning expert. So one of the few who are dually educated and trained that we will all rely on to bring this dimension into clinical practice. So Rob, welcome to AI Med. So let's hear about your sort of perspective on explainable AI.
Great, thank you, Anthony. Can you hear me okay?
Yes.
Great, lovely. Okay, thanks for the introduction. I feel like you've set me up for a fall by describing me as an AI expert, but I'll do my best. So I'm going to talk a bit about explainable AI in clinical practice, and I'm actually going to play something of a devil's advocate to what Dave was just talking about by describing some of the downsides of deep neural networks. Dave actually beat me in a push-up competition in a bar in Florida once. So once I found out I was doing the talk after him, I couldn't resist doing something that might be slightly controversial. For anyone who's not familiar with the idea of the black box effect, I suspect most of us are, but it's the phenomenon whereby when a system or program or algorithm becomes sufficiently complex and non-human in its functioning, we can no longer consciously comprehend its internal logic, at least not exhaustively. And so you get this effect where stuff goes in, stuff comes out. What happens in the middle can remain something of a mystery. Now, the black box effect isn't a dichotomous thing. It's a little bit more subtle than that. And so this slide gives you a slightly more nuanced overview. In short, the more powerful your algorithm, the less explainable it tends to be. And Dave has already touched upon the fact that you need lots of data to feed these more powerful types of algorithm. And you'll see in the top left of this slide that deep learning algorithms based on deep artificial neural networks. They are the cutting edge in modern AI technology, but they are also the least explainable and the most data greedy of the algorithms that we use. Now, I had a couple of slides just to illustrate why the power of deep neural networks and why we sometimes sacrifice explainability for sophistication, but I'm actually going to skip over these because I think Dave did a great job of illustrating some of these applications, and I'm keen to leave some time for discussion at the end. So what I'm going to go straight onto is talking about some of the downsides of having a computer system where you don't always understand exactly how it works. Now, what I'm not going to talk about is a propensity for errors, because whenever you have technology in a situation, things can go wrong. The problem with using black box type technology, and particularly deep learning technology, is that the error distribution can be less predictable than when you have a conventional computer program, which is to say it's harder to anticipate when and where things are going to go wrong. So I'm from a traditional software engineering background, and when I've written programs in the past, some of them have been deployed into the medical domain. If you know a particular thread in your program is mission critical, you have time to go over it with a fine-tooth comb and stress test it and rewrite the code until you're happy. And you know there are going to be some bugs in your program, but you can control where they occur. You can spend a bit less time on the user interface or the bells and whistles of your application. You can't do that in the same way with deep neural networks, which I've more recently been involved in developing. And I think these slides show a couple of examples of how things can go wrong. So in the top left of this slide, you've got an algorithm developed by Google, obviously have access to some of the brightest minds and the most significant resources of all technology companies in the world. Their algorithm, as you can see in the bottom middle frame, has mislabeled a picture of an Afro-Caribbean couple as gorillas, which is obviously deeply offensive, and it was a PR disaster for Google. And you can bet your life that if they'd developed this algorithm using conventional techniques, not that it would be possible to produce something so powerful that way, but they would have made pretty sure that their algorithm wasn't going to display any sort of outputs with racial connotations or sexist or ageist or anything like that. In the bottom right of the slide is a Tesla that was driving down the freeway on autopilot mode with a human in the driver's seat and failed to spot a large white truck crossing the road in front of it. And it failed to spot this so spectacularly that it didn't even apply the brakes and went under the truck at full speed, and the driver was decapitated. Now, this is perhaps less an example of not being able to predict where things are going to go wrong, because any technology will get buggy in a complex dynamic environment. But this illustrates the fact that there's something morally repugnant to humans about AI technology going wrong and causing harm to mankind. So self-driving cars have on average significantly fewer accidents than their human-driven counterparts, but the AI technology that powers them is perceived to be something more than simply an instrument of human will. It learns for itself. It operates in a mysterious black box type way. And so when a self-driving car has an accident, like the Uber car in Arizona that ran over pedestrians, another example, it makes international headlines, whereas people are getting hit in every town everyone in this audience lives in every day, and we don't make a big deal about it. And that has important implications for the medical domain, of course. So I want to run through a couple of quick thought experiments. I'm also involved in ECG research here. I want to show you 3 scenarios where you might use deep learning technology to undertake ECG analysis. So in the scenario 1 is a true sort of end-to-end deep learning diagnostic tool with a black box effect. So ECG signals go in, diagnosis comes out. And they've also used an example showing an anterior STEMI. So here there's ST elevation in the anterior chest lead, reciprocal or appropriate limb lead elevation. This is a classic STEMI. But if I were to say to you that your brand new intern was in the emergency department in the middle of the night and based their clinical decisions upon this label here, with no explanation given as to why this diagnosis was arrived at by the technology, and your intern you were pretty sure wasn't qualified to overread the ECG properly, I wonder how comfortable most of us would feel about standing up in court and defending what happened next. Scenario 2 shows us one of the tricks you can use to sort of lift the lid to a certain extent on the black box effect. This is, I don't know how well you can see the slide here, but there is an ECG trace under this heat map. So this is an attention map, also known as a saliency map or a class activation map. It shows you which parts of the ECG the algorithm is assigning most weight to when it's making its diagnosis. So if we're talking about an ischemia detecting algorithm, you can see that the STT segment's lighting up quite nicely, particularly in the bottom frame. So this gives you some reassurance that the algorithm is approaching the diagnostic task in a sensible way, because one of the key drawbacks of all things machine and deep learning is that these algorithms are fantastic at learning correlation, but they cannot discern causation. That remains unique to human intelligence, and that's very, very important. Scenario 3 then is where we've used a deep learning algorithm to simply extract high-level features, and then we've applied a logic-based diagnostic component on top that gives you very transparent reasoning. This limits the power of the deep learning component of this tool to simply a feature extraction mechanism, which can be significantly disadvantageous because, as Dave talked about, there's evidence emerging just from the world of ECG interpretation of algorithms that can detect incipient atrial fibrillation and other important conditions. And there are algorithms in the world of radiology that appear to be able to diagnose incipient Alzheimer's disease. And if you restrict these algorithms to simply extracting features, you lose the power to push the bounds of human understanding. But of course, you then gain explainability in exchange for that. The other issue here is that these features, R waves, P waves, ST elevations, they're actually high level in features themselves that are comprised of they're composites of other lower level features. So if you use a deep convolutional neural network with 30 to 50 or even more convolutional layers, what you're doing is you're drawing out 30 precedents to the point where you get this feature ST elevation. So where's the arbitrary point when you say, okay, I'm happy with my algorithm extracting features without being able to explain itself to this point, but from point X onwards, I want my algorithm to tell me what it's doing. Where does that point lie? Where's the generalizable rule here? Because it will change between arrhythmia detection and ischemia detection. It will change between ECGs and MRIs and CTs and histopathology and so on. So here's the proposal that I have for the audience today, and this is perhaps more to provoke discussion than because I'm wholeheartedly behind it, but I think there's some rationale. We're talking about AI applications that we're going to deploy into a very human-centric environment. Our day-to-day practices are built around human clinicians and patients. Our medico-legal and governance frameworks are based upon human behavior. And of course, the human brain has a very substantial black box effect. So much of our cognition is subconscious. So that's already accounted for in the way we approach day-to-day medicine. So if I'm taking a handover from an A&E doctor who phones me and says, oh, I've got a patient here with anterior ischemia, can I send them up to CCU? I'm going to say, well, just tell me a little bit more about how you've reached that diagnosis. And they're going to say, well, there's dagger-like T-wave inversion in the anterior chest leads. And they'll tell me about the other ischemic features. And at that point, I'll say, yeah, okay, I buy it, send them up. I'm not going to say to them, okay, describe to me exactly how you've identified the T-wave here. What are the morphological features that have led you to conclude that this inflection from the isoelectric line is a T-wave? That sounds ridiculous to any clinician, but that's the point where we've decided it's acceptable to allow the human black box effect to play out. And then from the point where you actually marry up the locations of the T-wave inversions to the diagnosis of ischemia, I expect a lucid, conscious, logic-based explanation for that. And maybe that's not a bad rule of thumb for what we should expect from AI algorithms in clinical practice. Just moving forward then to talk about how that's impacted my own research. As I said, I want to leave time for discussion, so I'll just talk for a minute or two longer. A lot of my research has been in the field of trying to detect ischemia better than human experts. So to use these powerful analytical tools that deep neural networks represent to see subtle patterns within the complex ECG data that will lead us to conclude that there is ischemia present before a human can do so. And that's a very plausible idea that is possible to happen, because the human eye has very limited resolution. In fact, the human mind has very limited capacity for complex data processing. But recently, after a couple of experiences, or well, I suppose a few years working with deep neural networks, I've actually shifted back a step, and I've said, hang on a second, let's move back towards addressing what Gorovitz and McIntyre, they're the psychologists that Atugwandi quotes in his book, they would call errors of ineptitude rather than errors of ignorance. Those are horribly harsh terms, but they're talking about the fact that sometimes patients die and come to harm because medical science fails them. If you've got a small cell lung cancer, we probably can't give you life-saving treatment if it's beyond the point of operability. That's a failing of ignorance. We don't know how. A failing of ineptitude is when you rock up to the ED and you wait 30 minutes for your ECG that shows a STEMI, by which time you've lost a lot of your anterior myocardial wall if it's an LAD infarct, and you're consigned to a lifetime of heart failure. That's ineptitude, because we knew what to do, we just didn't do it right. So my research has stepped back towards the latter problem, of which there is plenty. 10,000 patients are thought to die preventively in UK hospitals alone as a consequence of medical error. So I am working on an application that can look at photographs of ECGs and reach robust, approaching expert level diagnosis, but I'm not hoping to supersede experts. So how we're using deep learning for this, a deep convolutional neural network takes the photograph of an ECG and segments out the relevant waves, and then we apply a logic-based layer. I haven't actually included it in this example to say, well, every QRS complex is preceded by a P wave at a regular interval, so this is sinus rhythm, for example. And the interesting thing that experience we've had, and this is the last 60 seconds of talking, is that because ECG data generally exists, you get the ECG that's stored somewhere and you get a diagnosis stored with it, but no cardiologist ever goes through and segments out the P wave, the PR segment, the QRS segment. And frankly, when I decided I was going to go down this road, I was way too lazy to go through thousands of ECGs and manually segment them myself. So I developed an application to simulate ECG images. And in doing so, found myself in a situation where I had complete control over the curriculum, as you call it, of the deep neural network we were using. So we trained it on simple things first, got progressively, faced it with progressively more complex challenges. And we were able to really exert a high level of control over the way it learned. Almost, there's a very vague parallel to be drawn with educating human children. That's not usually the way I talk about my children, educating human children. But and then what we discovered was actually the segmentation algorithm that has been applied to this real world photograph that, as you can see, has some ink stains and other artifacts, has never been trained on a real world ECG. So there's a few interesting branches to the research we're doing, but some of this is probably a talk for another day. I will stop there because I hope there's going to be plenty of discussion, and I want to leave time for that. And thanks for listening.
Thank you. Excellent. Maybe David, you can come back on, and we'll have literally 2 minutes for a discussion before our break. I think it's an exciting time to see some real applications of machine learning, deep learning. David, are you still there? Okay. So maybe in a minute, because we're running out of time, Rob and David, we'll start with Rob. Just give us one major takeaway from your experience in this relatively uncharted dimension of machine and deep learning.
I think the major takeaway I've had, it probably is that problem with correlation versus causation. There was one particular study I got badly caught out by an algorithm. We think in hindsight it was detecting the background electrical activity of a fluoroscopy machine, which apparently occurs at about in the 400 hertz range. I didn't know that at the time. And it was correlating that with ischemia. And we thought we'd set up a really robust study, and we had it quite extensively peer reviewed and all had gone well. And then we went back and made a couple of tweaks and discovered that actually our algorithm was diagnosing ischemia based on something that was not associated at a physiological level with ischemia. And that was a really sobering experience for me.
Yeah. No, so the human cognition still needs to be part of the process, even though you have more and more sophisticated machine and deep learning. Dave?
Well, we had the same thing. We've had the same thing occur where identifying beats in a string of beats, identifying a morphology, and we realized that our beat identifier was using the beats around it. And one of our engineers who came from Google said it's a classic.
Yeah.
There's a deep neural network that identified wolves. but it identified anything as a wolf if there was snow in the background.
Right. That's a famous one. Yeah.
So, that is,
yeah.
It wasn't the thing you were interested in, it was the surrounding. And I've been told that this is a problem, and it's why you have to be careful. These are not magic.
But it's a good thing that humans are still required for, I think, intelligent use. And I say artificial intelligence and human cognition is the most powerful dyad. So, okay, with that, we're going to take a 10-minute break. And again, please orient yourself to the Discord software that is coupled with this webinar. It's been a fantastic discussion as well as a good educational opportunity and exchange of learning. So we'll see you in 10 minutes. Thank you, everybody.
Good to see you, Anthony.
Thank you, Dave and Rob. Yeah. Oh, by the way, I just want to thank our, the reason why all the clinicians are getting CME credits is we have a very generous donation from IBM Watson Health, as well as Surgisphere that you'll hear from later. So thank you, Watson Health and Surgisphere. So we'll see you in 10 minutes.